So today we will talk about microcontrollers' energy modes. So I'll share my screen now, and I will have a data sheet on this screen of the microcontroller that we will be using in our labs. So we are using a microcontroller from Silicon Labs, EFM32, Giant Gecko series. But all microcontrollers are basically built the same way. And if you took, for example, STM32 microcontroller, it would have almost identical principle of working. And now I will try to explain to you why everybody isn't using microcontrollers from, for example, Arduino family, or why isn't everybody just using some high level programming language, or why isn't everybody just programming in Python? Why do we need to program in this low level C programming language? And the reason is that the lower language we use, the more precise control we have over microcontrollers' energy consumption. um, and all of the microcontrollers are built in a very similar way. And older microcontrollers and newer all have the same principle. And it is the following. We have high frequency clock source. Most microcontrollers have a built-in high frequency RC oscillator. I'll try to zoom in a little bit. And so when you turn on a microcontroller, it automatically starts its built-in high-frequency RC oscillator, and it oscillates at, for example, 1 megahertz or 14 megahertz. So it can do 1 to 14 million instructions per second. And this clock source goes through this clock switch, so you can switch between internal oscillator and more precise external oscillator if you have connected it. And this oscillation goes to this high frequency clock wire, and it is, for example, connected through this prescaler to core. Where is core? Here it is, sorry. It goes here, high frequency core clock, and it goes to high frequency core clock CM3. So our microcontroller uses Cortex M3 core. So basically just this clock goes to core. And in most situations, we don't really use a prescaler here. We want our microcontroller to run at maximum speed. So whatever high frequency clock we have at input, usually it's just the same as the frequency for the core. So, and when the core is turned on, it just executes our code. Whatever we have written in the software, it will just do that thing, right? And in devices that are constantly powered by, for example, grid electricity, the devices that are just plugged into wall socket that have 230 volt power source constantly, usually the microcontroller just works at this high frequency and we don't care about anything. And that device can be built by any microcontroller, by any processor, it just works. But as soon as we want to use battery as our primary energy source, we don't want our high frequency core to be running all the time because it consumes energy. How much energy it consumes, we can check out in the chip's datasheet. Here is electrical characteristics, current consumption, and here we can see that at different frequencies, we have different power consumption data, and this shows how many microamps per megahertz we have. For example, if we are running, when we turn on the microcontroller by default, it runs at 14 megahertz from high frequency RC oscillator, and it consumes approximately 209 microamps per megahertz. So we need to multiply this with 14, and then we get the uh, total power consumption, and let's just do it right now. So 14 megahertz times 0.209 milliamps is, this microcontroller consumes almost 3 milliamps when it's running the code, right? So, that's just what we need to know. And if we want to, for example, do some communication through UART, or if we are running some timers, as we studied in the previous lessons, then we need to add extra energy consumption. It is written here, for example, if we have a timer running, then it adds extra 7 microamps per megahertz. So for example, so for this, we would need to add 7 times 14, um, so 0.0, approximately it's 0.1 milliamp extra energy. And if we're running UART, so another 3.4 times megahertz. So all of these peripherals add to the power consumption. And if we, for example, have a battery, let's say we have, um, these AA size batteries. We can check out on the internet, and you will see that their typical capacity, for example, for alkaline, is approximately, let's say, 2000 milliamp hours. So if we have 2000 milliamp hours and we divide by 2 milliamps, sorry, it was 3 milliamps, for example, 3 milliamps, we get 666 hours divided by 24 hours. It's just 27 days. So if we had a device that was running from at 3 milliamps all the time, we would need to change the battery every month. But as you know, your wall clock, you only maybe change the battery once a year, maybe once several years. If you have a TV remote, it also doesn't have to have batteries replaced every month, but maybe once every several years. So when we are using battery power, we need to cut down the current, and it is done in the following way. All microcontrollers have a special instruction. In some microcontrollers, it's called just sleep. In some, for example, in ARM Cortex, it's called wait for event or wait for interrupt. And it basically turns off the high frequency clock. Also, the code pauses, it just stops executing code, and it goes to low energy state. And in low energy state, this all of these peripherals are automatically turned off, and it consumes something like 1 microamp only, right? So let's check out. But what we need to notice is that as soon as we switch off this high frequency oscillator, everything that was running from it also automatically stops. So high frequency oscillator powers our timers, timer 0 to timer, I don't know, 4. It also powers the I2C interface. So I can zoom in. So I2C interface also runs from high frequency clock. So if we pause the microcontroller, also these timers stop, and also the I2C stops. What else? Uh, this dynamic memory access peripheral also pauses, but we don't really use it that much. Here is also USB. It also stops if we had USB active. Also, where are UARTs? So UARTs, we can select clock from several sources. Oh, these are low energy UARTs, but where are high energy UARTs? Timer 1, 2, 2, 2. I can't spot it, but generally UART is also running from high frequency clock, so it also stops. So if we are using printf to print out messages and we put microcontroller to sleep, also printing out messages stop. It's not really that bad because usually when microcontroller sleeps, nothing happens, so we don't have any messages to send. But in general, if we want to send the messages, the CPU is in active state, sending information. Okay, so knowing this, we can also check out the table of energy management unit. It's called energy management unit. In the microcontroller, it's a block that controls the peripherals. And this microcontroller basically has 5 different energy modes. Okay, we have a question. Oh, just yes. 5 different energy modes. And energy mode 0 is basically everything is working, everything is running. So the microcontroller does our code. I don't know, maybe it's blinking LEDs, writing some text on print or something like that. It just works actively. Maybe it does some calculations and so on. And basically in energy mode 0, all the peripherals are able to work. We can have LCD showing some texts and timers running, analog to digital converter running, and so on. So everything works. But this also consumes all of the energy. It consumes most energy compared to other modes because everything is running. And then the next energy mode in all microcontrollers it exists is when the peripherals are running, but the microcontroller's code is paused. For example, you can say, I want to send some information over UART. I want to send some information out, but while it's sending, I don't have to do any calculation, so I could just pause the microcontroller, but I can leave UART and everything else running. So this energy mode 1, it drops the microcontroller's power consumption by something like maybe 80%. It drops it to a couple of maybe 1 milliamp, but it saves some energy. But it is also not considered low energy mode. It's high energy mode. It just consumes less energy because MCU is paused. But all of the peripherals are working. So you are sending data back and forth. All the timers are working. PMW is working and so on. Next energy mode is energy mode 2. And this is the one where the fast clock is switched off. So everything that is running from a high frequency clock is paused. So microcontroller is sleeping, but also UART is sleeping, I2C is sleeping, um, also analog to digital converter is sleeping, so you cannot do these things. And before entering this mode, you need to make sure that all of them have completed their tasks. You cannot, for example, send data over UART to computer and then suddenly go to energy mode 2, because then the data will not be transmitted. It will be just abruptly paused. So usually in the code, you would write a simple line of code that while we're sending data, we wait, for example, in energy mode 1, and once the data transmission is complete, we go to energy mode 2. And energy mode 2 is good because it leaves the low frequency clock running. Let's go to our clock management unit again. And we see that we have a second clock domain, which is called low frequency RC oscillator. It is built into the microcontroller, but we can also attach an external low frequency oscillator, a crystal. We can just buy it for a couple of cents and just solder it, connect to the pins. And then some peripherals can run from these low energy clocks. So these peripherals keep working even when we have put microcontroller to sleep. And which peripherals are they? So we can see here all peripherals that start with LE basically are the ones that can be run from low frequency oscillator. For example, real-time clock, and this is the important one. The real-time clock is usually left running so that there is some source that wakes up the microcontroller when it needs to be woken up. Low energy sense, there is a special peripheral, low energy sense, which can help do some sensor measurements while the microcontroller is completely sleeping. Also, low energy timer. So there's one timer that can be run from low energy mode, so you can also have some uh, pulse width modulation even with a sleeping microcontroller, because generally pulse width modulation and driver controls are high frequency tasks, so they cannot be run from the batteries. But in this case, one of the timers allows for it. And also, if you have liquid crystal display, and in our development kits, we actually have LCD, you can also have LCD running even with the microcontroller sleeping in low energy mode, and also pulse counter. So these are the low energy things, and also low energy UART 0 and 1, they also can run at low frequency, but their maximum data transmission speed is also limited to just 9,600 symbols per second. So at high frequency, they can, from high frequency clock, they can run at maximum speed. I think it's something like 1 megabit per second. But if we're running them from low frequency oscillators, then we have to also slow down their data transmission speed to 9,600. So low frequency. So these peripherals are usually run from low frequency oscillator. And the reason is that when we tell microcontroller to go to sleep, it stops code execution. It just pauses, and then you need some signal to wake it up to let it restart doing the things that it's doing. And usually for that, a real-time counter is used. So you set up real-time counter to, for example, have an interrupt after 1 second, and then you tell microcontroller to go to sleep, and after 1 second, or maybe if you want after 1 minute or 5 minutes, the real-time clock will wake it up, and the microcontroller will restart doing the code from the place where you put it to sleep. So this is why in energy mode 2, where do we have it? In energy mode 2, high frequency stuff is sleeping, it's switched off, but low energy things are still running. For example, real-time clock, real-time counter, liquid crystal display, low energy UART, low energy timer, pulse counter, and also analog comparator is also working. There is this thing, analog comparator. It works by comparing two voltages, and it can be, for example, used to detect when some voltage drops. For example, power supply voltage drops, you can wake up the microcontroller and do something maybe. And energy mode 2 basically has this low energy clock running. Energy mode 3 is even deeper sleep, and some components don't work. For example, liquid crystal display and low energy UART. But other things can still work if they are running from an backup 1 kilohertz ultra low frequency oscillator. And here's the thing, in energy mode 3, the low frequency crystal is switched off. So in this clock management unit, these low frequency RCO or low frequency crystal, they are switched off, but there is another clock which is ultra low frequency RCO, which runs at approximately 1 kilohertz. And if you have connected your peripherals to run from this clock, it's still running in energy mode 3. And typically you would connect Watchdog to it, and sometimes also real-time clock, right? So, and this Watchdog peripheral is a special counter. So you set it up, and if you don't reset it, it will restart your microcontroller. And it's meant to restart your microcontroller completely, like power cycling it. If, for example, your code has some fault and it hangs. So there's this watchdog peripheral. We will also be using that. So if your microcontroller has a bug and it just hangs, this watchdog timer will reset it, restart the whole program after some time. You can set it to, for example, up to several minutes, and then your microcontroller occasionally resets it. And if it hangs and it cannot go to the place where it resets it, then Watchdog will reset the whole microcontroller, and you will restart the code. So basically, energy mode 0 means that everything is running. Energy mode 1 means that everything is running except core, the code execution is paused. Energy mode 2 means that high frequency clocks are switched off and low frequency clocks and ultra low frequency clocks are running. And energy mode 3 means that only ultra low frequency clock is running and all higher speed clocks are switched off. And finally, energy mode 4 means that all clocks have been stopped. Energy mode 4 means that all clocks are stopped, and basically nothing can wake the microcontroller up, except if you cycle its power or you press reset pin low on the microcontroller. And there are also a couple of pins that can also be used to wake up the microcontroller. But basically, energy mode 4 is used like complete shutdown. And you might ask, why do we need energy mode 4, which basically stops the microcontroller entirely? And the reason is this. It is used, for example, in car remotes or some other device where you press the button, the device turns on, does something, and then you don't need it to do anything else. And it basically just shuts itself completely off. And then when you press the button next time, it turns on, does something, for example, opens the gate, and when it's done, it just goes to sleep and shuts off completely. So in energy mode 4, only reset can restart it, nothing else, very rare occasions. And for example, generally in my career, and maybe in your careers as well, you will actually mostly 99% of the time will only use energy mode 0 and energy mode 2. So you will, in energy mode 0, you will do something, do analog to digital conversion, some signal processing, some calculations. And then when you have done everything and you don't need to do anything more for, for some longer period of time, you will set up a wake up interrupt in real-time clock and just go to energy mode 2 and sleep. For example, typical application, some wireless sensor, for example, temperature sensor, needs to report temperature every 5 minutes. So it wakes up in energy mode 0. It samples the temperature, for example, through I2C interface from a temperature sensor, which is on the board. Then it sends the temperature through UART or through wireless, and then it has to go to sleep for 5 minutes. So you just set up a real-time clock to wake it up after 5 minutes and go to energy mode 2, and the microcontroller is shut off. The only thing that is running is real-time counter, and after 5 minutes it will wake up the microcontroller and you will start it over again. And let's check out the energy consumption for the low energy peripherals. So as we can see, power consumption, current consumption here. So in energy mode 0, as I said, almost all of the energy is consumed by the core. So energy consumption is approximately 200 microamps per megahertz. Here is energy mode 1 current consumption. So core is paused, but the rest of the microcontroller is running. So here you have approximately 83 microamps to megahertz. So let's calculate 83 times, for example, 14 megahertz times 0.001 from microamps to milliamps. So approximately 1.15, 1.16 milliamps in energy mode 1. So from 3 to 1 milliamp, it's not such a big difference. So some people just don't use this energy mode 1 at all. And energy mode 2, when you put the microcontroller to sleep and have only real-time clock running, as you can see, the current consumption drops from 1 milliamp to 1 microamp. And that is a significant, very, very big energy saving. So let's check out. Let's say we have the same AA size battery with 2000 milliamp hours. And let's say we put the microcontroller in energy mode 2. Let's take the worst case scenario. It consumes 1.9 microamps, so divided by 0.0019 milliamps. Now we have 1 million hours of work divided by 24 hours per day. It's 43,000 days divided by 365 days per year. We get 120 years of device running at this sleep current. In reality, it will not work for 120 years because the battery has internal self-discharge. It's a chemical compound, and it slowly discharges in its own. So the chemical just reacts slowly with itself, and its capacity drops just even disconnected. But the microcontroller consumes almost nothing. So in the battery information, you can actually check out its self-discharge. So a battery, let's check out self-discharge. So lithium ion chemistry has approximately 3% per month self-discharge in the first month, and then something smaller in the next months. So actually not great. But these alkaline, for example, alkaline battery, here it says self-discharge 0.3% per month. As a result, just self-discharge of this battery will cause it to go bad in something like 10 years. But the microcontroller's power consumption will be significantly smaller. So, a device can work 10 years from a single battery. So energy mode 2 current, very small. However, if you check out energy mode current in the next line, you might ask, well, what is this 21 microamp? The problem is that, as you know, when silicon is heated up, it has more ionized electrons, so it has a leakage current. So even though all the field effect transistors are closed, there is some leakage current that flows through the microcontroller, even when it's not doing anything. And if you heat up a semiconductor, it starts to conduct electricity better. And actually, at low temperatures, it has lower leakage, and at high temperatures, it has higher leakage. So you can check out at 85 degrees Celsius, it will have higher leakage current of 21.5 microamps. So this is the problem. So at high temperatures, you just have to realize that the leakage will be higher. At low temperature, lower. And here we can also check out the energy mode 3 current. So again, when low frequency oscillator switched off, it consumes even less energy, but at high temperature, still significantly more. And energy mode 4 current, also here. So energy mode 4 consumes little energy in high temperatures because all of the microcontroller basically disconnects itself from power supply, and only reset button connects it back to the power supply internally, and it starts to work again. Here we can also see the current consumption as a function of supply voltage, and also as a function of temperature. And as you can see, at low temperature, lower power consumption, you heat it up, more leakage current, and at higher temperatures, higher current. And also at lower voltage, consumption is smaller, and at higher voltage, the power consumption is bigger because of the leakage and resistance. Okay, so where were we? Current consumption here. Let's compare power consumption of this chip to something a little bit older. So this chip that we have here at hand is EFM32. It's ARM Cortex chip. It's very new technology. It has very small transistors, but let's compare its power consumption to a very old chip. So Atmeg 88 is a microcontroller from AVR, which became very popular in years 1995 and 1996. And it's basically the heart of Arduino. Arduino started from this microcontroller, basically. And it's still used in many devices, even though it's really old. So let's check out the datasheet. Okay, complete datasheet. And let's check out its power consumption. Yada, yada, yada. Temperature range the same, speed grade, low power consumption, 15 microamps. Okay, we can see that the power consumption at 32 kilohertz low frequency clock. This is active mode. Power down mode is smaller. So where can I check it out? Power consumption. I haven't checked this data sheet this year, so the active power supply, let's check out. So, so the chip is running at 1 megahertz after reset by default, but you can increase its internal speed up to 8 megahertz, and you can connect an external crystal to make it run up to 20 megahertz. This is why, for example, also in this EFM32 chip, we have this option to switch between high frequency external oscillator and high frequency internal oscillator. Internal oscillator only runs up to, for example, 21 or 28 megahertz. But if you can connect an external oscillator, you can make it run up to, for example, 48 megahertz. And the same is for this 80 mega 88. Internal oscillator runs up to 8 megahertz, and external oscillator can be up to 20 megahertz. So you get higher speeds if you have connected external oscillator. And I want to check out the sleep current supply. Idle, power down, supply current. Disabled. Timer enabled. So as you can see here, power down supply current usually is when we are talking about real-time clock running. Let's see. So watchdog timer is enabled, so there is a low frequency timer running. And as you can see, sleep current is 4 microamps, and at higher voltage, it can increase up to almost 10 microamps. But as you can see, temperature doesn't really make such drastic changes. So at 25, minus 40, and 85, the current consumption almost stays the same. Whereas in our modern, much newer microcontrollers, at room temperature, the power consumption in sleep modes is really small, approximately 1 microamp. And at high temperature, it's really big. It's up to 20 microamps. That's a lot. And can you guess why it's true that old processor has lower leakage current, lower power consumption in low energy modes at high temperature, whereas the newer processors have higher power consumption at high temperatures? Why is that the case? So the reason is that newer processors use smaller transistors. So, and if the transistor is smaller, it consumes less energy, and you can run it at higher speeds. You can turn it on and off faster because it's so small. It has so small parasitic capacitance that you can run it very quickly. So smaller transistor means that you can run it more quickly, and it consumes less energy, and it heats up less. So you would think it's better. But because it's smaller, its drain and source are located closer together. If it's smaller, the source and drain are located much closer together, so the leakage current is higher. So this is a fun fact, that old microcontrollers have bigger transistors, so they consume more power and run more slowly, but their leakage is much lower than the newer chips, and especially at high temperatures. At low temperatures, there's almost no difference, but you heat up the MOSFET, and the leakage current for smaller transistors becomes really, really big, 20 microamps. It's 20 times bigger than at room temperature. So as a result, you might see that in high temperature industrial applications, people are still using this almost 30 years old microcontroller Atmega 88 from from Atmel, now microchip, the same that is used in Arduino, because it's older technology. And these 80 mega 88 chips have a um, transistor size 165 micrometers, whereas these newer processors, for example, ARM Cortex processors, they maybe have, for example, 50 nanometer technology. So transistors much smaller but much higher leakage current. And you just have to take it into account. If you know that your device only works at room temperatures, you can take this ARM Cortex microcontroller and don't worry about it. But if you have automotive application, then oftentimes people choose these older, more robust processors. Okay, so the next thing that we need to talk about with these clocks. There is also one thing that is called backup real-time clock, which can also be run from ultra low frequency RCO, and it still works. So I don't know, maybe you have some questions about microcontroller energy consumption in different energy modes. Okay, so if no more questions, now let's check out why do we have two clock sources at high frequency and two clock sources at low frequency? Why do we have high frequency RCO and high frequency XO and low frequency XO and low frequency RCO? So microcontroller has built-in high frequency clock and low frequency clock. So basically you can take the microcontroller and you can immediately put it to work, and it will perform high energy tasks, and it will go to sleep, and it can wake itself up after some time with real-time clock, and it can consume very little power. So why do we have these external oscillators available? And the reason is the following. Um, we need to check out the precision of built-in oscillators. So low frequency oscillator that is built into the microcontroller, the best place to look is right this graph. And the problem with built-in oscillators is that they are not very precise. First of all, they have low precision and they have high dependency on supply voltage and on temperature. So if you increase, so their nominal values are given at 3 volts, but if you have power supply that is from 2 volts, as you can see, instead of 32 kilohertz, it has frequency of 38 kilohertz. So that's a big difference. So you cannot have, for example, a clock that shows you time, and the time is running something like, I don't know how many percent. So 38 divided by 32. So almost 20% faster. So you build a wall clock, it shows you that it's, for example, 15 and 19 minutes, but the clock at low voltage runs 20% faster. And also it's temperature dependent. So at higher temperatures, it runs faster, and at lower temperatures it runs slower. So yeah, if you only use it at room temperature, it will be just fine. But if you are running it at high or low temperatures, high and low voltage, it's very not precise. So yeah, at 2 volts, it's almost 40 kilohertz. So that's not precise at all. So this is the reason why if you need high precision, you go online. For example, you can buy these external oscillators from Wood Electronic, Passive Components, or any other manufacturer. You just check out by the price. So you select watch crystals for low frequency, and they are all historically 32.768 kilohertz. And you can just basically select the package. You want it like a square, 1.6 times 1 millimeters, or 2 by 1.2, or 3.2 by 1.5. This is a very, very popular size. 3.2 by 1.5 is very common. So it's probably the cheapest one. And then these big packages, and also this watch type crystal. This is probably the cheapest package. These two round cylinders are the cheapest packages, but the problem is that they're very hard to solder to the board. We were using these, and oftentimes during manufacturing, one of these legs was up in the air and didn't solder to the board, so the devices didn't work, and they had to be manually fixed. So I don't recommend these, but these are really, really cheap. What I do recommend is this 3.2 by 1.5 size, or maybe something smaller. These solder very well, so no problems with that. And if you select them, you can see the frequency precision, and also the temperature and the load capacitance. Sometimes the microcontroller datasheet specifies what load capacitance it accepts. Sometimes it doesn't, so you can pick any one of these, but this 12.5 is somewhat very popular. And so oftentimes this 12.5 is just the most common, and basically everybody uses that. Let's check out these watch crystals. These watch crystals are almost all 12.5. Smaller capacitance means that it will use less energy because you need to charge and discharge smaller capacitance, so less charge is wasted. But not all microcontrollers support these lower things. Lower capacitance means higher frequency, so it has to take it into account. So this 12.5 is the most popular. And let's check out the precision of this crystal, for example. So 32.768 kilohertz is the frequency. This is just historically selected because if you divide it by 2 to the power of 15, its pre-scaled frequency is 1 hertz or 1 second. So you add a 15-bit counter, and when it counts, when it overflows, you increment the time by 1 second, and it works as a 1 second counter. It's just if you wanted to make a crystal which has internal uh, resonance frequency at 1 hertz, it would be very, very big in size. As you know, the bigger the material, the lower the frequency. So this was a good size and good frequency uh, fit historically. And the manufacturing precision is plus minus 20 ppm. So if we want to calculate the effect on the frequency, what you have to remember is that this number is given as ppm, parts per million. So you need to multiply this number with millions of hertz. So for example, you have 32.768. You multiply it by, okay, whoops. So how many millions? 0.032768. These are millions multiplied by 20 parts per million. So its imprecision during manufacturing, sample to sample difference will be only 0.65 hertz. So the difference is, very small. The second thing that you can check out is aging. So after some time, it may drift a little bit, but it's just 3 parts per million max in the first year, and usually no more than 2 more ppms per the next rest of its life years. And you can also check out its temperature dependence. And as you can see, they are built in such a way that at 25 degrees, the frequency is what is nominally said, but unfortunately, when the crystal cools down, it contracts, it becomes smaller, and when it heats up, it expands and becomes bigger, so its resonance frequency changes. And it's built in such a way that its frequency changes as, this parabolic line. So unfortunately, at, for example, minus 50 degrees Celsius, it will oscillate at minus 200 parts per million lower frequency. And when it's heated up, for example, to 75 degrees, it will oscillate slower by 100 parts per million. So you multiply these and the frequency changes a little bit. And that's not great, but the difference is still small. So 100 ppm would basically mean that it would be something like maybe 3 hertz difference. So the difference is still small. Well, okay, let's calculate the worst case scenario. We have this crystal. It is, for example, it has plus 20 ppm imprecision manufacturing error, 5 ppm aging drift, and for example 100 ppm because it's put at 75 degrees or minus 25 degrees ambient temperature. So we count all these ppms together. So 20 ppm is manufacturing imprecision plus 5 ppm aging, 3 in the first year and another 2 in the next years. Usually it doesn't drift by aging more than that. And plus, for example, 100 ppm. So it's a total of 125 ppm max deviation between, for example, minus 25 degrees and plus 75. Now we multiply this by the millions of hertz. So 32 kilohertz is 0.032 million hertz. 768. And as a result, unfortunately, the frequency can shift by minus 4 hertz approximately if we drop this thing. It's 4 or 4.1. So instead of 32.768, it will oscillate at 32.768. It will oscillate at 32.772.096. So there's a little bit of difference. And this is why if you have a microwave or an oven, which also displays a time on the screen, after a couple of years, you will see that it starts to show a wrong time. In something like a year or 2 years, its clock kind of drifts away by some minute. But the difference is very small, so it only causes a shift by something like a minute per year, so you don't really worry about that much. But if you look at internal low frequency oscillator, its precision is very bad and its drift due to the temperature and voltage is very bad. So these are really like night and day. So here we have 38 kilohertz, 32 to 38, and here just 4 hertz difference at external clock. So if you are building a device that needs precise timing, which features any kind of clock functionality, and the device will have big temperature swings and maybe supply voltage swings, you need to use external oscillator. You just have to pay the extra 15 cents and solder it on the board, add it to the board, and use external oscillator. But if you only need not very precise clock, and the device will always be at room temperature and voltage will also be constant at approximately 3 to 3.3 volts, then you can also use the internal oscillator and save some money. And a little bit of information about how to connect external oscillator to the microcontroller. So the microcontroller, if we check out in its datasheet, usually it has special pins that normally are used as general purpose input output, but they have alternate functionality for external crystal connection. So L, let's search for letter L, low frequency crystal oscillator pins. You can see here that if you want to connect low frequency external crystal, you connect it between port B pin 8 and port B pin 7. Two pins are dedicated for that. And if you want to use internal one, you can use these pins as anything else, as GPIOs to turn on and off LEDs and so on. And how to connect them? You connect them in the following way. So the crystal, external crystal, its schematic symbol is like this. So it reflects the built-in way. There is a crystal and it's put between capacitor sheets, and as you put voltage, it contracts, and as you release voltage, it expands. So it starts to oscillate and it resonates at some frequency, and its oscillation is fed back to it, so it becomes a stable oscillator. But because it has some capacitance, there is this requirement that you also connect two capacitors to ground. It's just a classic schematic. Basically, all microcontrollers require it, that you have oscillator connected between MCU pins. In our case, it was port B7, for example, and port B8. And there are these capacitors to ground, load capacitors to ground, and they are like a function of crystal's internal capacitance plus the capacitance of the traces on the PCB that go from microcontroller to the crystal. And usually we want this capacitance to be as small as possible, so the crystal is physically put next to the microcontroller as close as possible. It's not put on the opposite side or opposite edge of the PCB. Usually it's put next to the microcontroller. And to calculate this C1 and C2, usually the formula, you can find it on the internet, usually is like this: capacitor number 1 equals capacitor number 2 is equal to 2 times crystal capacitance plus parasitic capacitance of the PCB traces. Let's check out. You can also Google it. So crystal load capacitance calculation, blah, blah, blah. And here is the formula. Sorry, I wrote it a little bit wrong. So it is crystal load capacitance minus the parasitic, not plus. Load capacitance minus, this is called stray capacitance. So I'll correct this. And usually the capacitance of the traces is just approximately 1 to 3 picofarads. So usually everybody just chooses 2 picofarad approximately. So it's something like 1 to 3 picofarad. And usually people just select the closest nominal value, and these capacitors, if you guess the capacitance of traces wrong, usually their impact isn't as big as to cause the system not to work at all. It will work. So if you're not exactly 100% precise, it's not that bad. Nothing bad will happen. It will still work. So if we know that very popular value of the crystal capacitance for these 32 kilohertz crystals is 12.5 picofarad, and then we assume that the trace capacitance is something like, for example, I don't know, 1 picofarad, then we can I'll just add this wave in front of it, approximately 1 picofarad. So these load capacitors are C1 equals C2 equals 2 2 times 12.5 minus, for example, 1 is equal to 12.5 minus 1 is 11.5. I can, and then 2 times 11.5 is approximately 23 picofarad, and the closest value that manufacturers offer is 22 picofarad. So very often in the circuits, you will see that the C1 and C2 is just 22 picofarad. So if the stray capacitance is a little bit bigger, then it perfectly fits. So if it was 1.5 picofarad, then this result would be exactly 22 picofarad. Because if you check out the catalog of capacitors of the manufacturers, then usually you cannot buy any value. You have to select. So we need something from 20 picofarad to 25 picofarad. And as you can see, you only have 22. So 20 and 25 don't really even exist. So 22 picofarad is the standard value of a capacitor. And so this 22 is very popular. And so this was for the low frequency domain. And for high frequency domain, let's say, again, the built-in oscillator of this microcontroller is up to 28 megahertz, but basically the chip is built in such a way that it can run up to 48 megahertz. It's just very hard to build a 48 megahertz RC oscillator. These RC oscillators, usually 30 megahertz is the limit, because RC isn't really the best way to generate frequencies. Crystals are much better. So to run it at 48 megahertz, you definitely need to connect an external high frequency external oscillator. And again, in the datasheet, you can check out to which pins you can connect it. So it is called high frequency Xtal. So you connect it to port B14 and port B13. I'll use the same picture here. So the second crystal connects the same way. So this is the crystal symbol. And here it's the same, two capacitors to ground. And now you will calculate yourselves what is the value of, I will call these C3 and C4. And let's just select, so in this data sheet, I checked out that the maximum frequency is 48 megahertz. I think it's also written in the beginning. Here you can see on Cortex M3 CPU up to 48 megahertz. So you need 48 megahertz crystal. So let's just check out again here. Quartz crystal here and 48 megahertz. Here again, you can buy these crystals at different packages, smaller ones, bigger, and then these things. These things are really big on the PCB. So these shapes are the cheapest. This metal, you have probably seen them in some devices if you have opened them. And these are good crystals, but they're very big. They are cheap, but they're big. They take a lot of space on the board, so mostly people would want to use something smaller. But unfortunately, smaller is more expensive. As you can see, these smaller crystals have 4 pins, but 2 of them just connect to ground, and they have metal cap, so connection to ground just shields it from radiating these noises out. So let's check out. We want 48 megahertz oscillator, 48 megahertz. Okay, we have 3 options. Not 3, sorry, something like 1, 2, 3, 4, 5. 5 options. And basically we can select how precise we want the crystal and how much temperature drift we can accept. So the first one is manufacturing precision. So they manufacture 1 million pieces and their precision from manufacturing is plus minus 20 ppm. And the second number is how dependent on temperature these things are. And so across the operating temperature, because of the temperature, they guarantee that the crystal will not drift more away than 15 ppm from minus 40 to plus 85. Here, this one, 30 ppm, and so on. So of course, more precision is more expensive, but the difference is usually not that big. And also, you can see that they have different sizes. They're just not visible here, but yeah, different sizes. And different load capacitance, so 18, 10, 8, and so on. And let's say we want to pick this one with 10 picofarad. 26, let's see, 26. Usually smaller capacitance means lower power consumption. So let's take this 8 for the sake of calculation. Let's say we want the crystal with 8 picofarad, plus minus 10 ppm, and plus minus 15 frequency stability. So if I tell you that the crystal is 48 megahertz and 8 picofarad, now your job is to quickly calculate the value of C3 and C4. And you can see the example here. So maybe you can calculate capacitance C3 and C4 values and tell them to me, and then we can check out if it's correct or not. Okay, so write in the chat what is the value of C3 and C4. So any guesses? Okay, 14 picofarad. That's true. Let's maybe calculate the interval. So 14 picofarad would be at 1 picofarad of stray capacitance. And what if the stray capacitance is 3 picofarad? How much would it be then? So I'll write down the answer was correct. So at 1 picofarad stray C3 equals C4 equals to 14 picofarad. Okay. At 3 picofarad stray capacitance C3 equals C4 equals 2. So 8 minus 3 is 5. 5 times 2 is 10 picofarad. So now let's check out what can we buy. If you open a website of any capacitor manufacturer, you will have a list of capacitances that are available. So capacitors, ceramic capacitors, general purpose, for example. And I don't know, let's check out this. And here we can see that the capacitance is, for example, 6.8, 10, and 15. You don't really have 14 picofarad. You can only select between 10 and 15, and 10 was kind of the closest one. We can also check out in Red Expert from this wood electronic in this view. So if you're looking for components and you want to, for example, use wood electronic components, they're a good manufacturer. Then you can use this Red Expert, which is, an easy to use component selector. I select that I need capacitance from 10 picofarad to 15, for example, picofarad, and it will show me the available products. And here I can select that I want the smallest size of 402. I don't need big capacitors there physically. I can also select that I want this NP0 material, and I can select the voltage rating. For example, I don't need bigger than 25 volts. Actually, the signal is something like one volt only. In this location, it's oscillating only at something like 1 volt. So these capacitors don't have to be like 100-volt capacitors. Smaller voltage, lower price. Okay, and the rest of them, I don't even know the difference. They all seem like totally the same. Oh, just the voltage difference. And 10 or 15. So I would use, for example, 10 picofarad capacitor at, for example, 10 volts. So this part number would be the one that I would use. Okay. Or for example, if I want more precision, I can also check out Murata sim surfing thing. So Murata is a big Japanese component manufacturer. They have more nominals usually than Wood Electronic, so you can use Murata. They're very good. Wood Electronic sends free samples, so I like them because they send free samples. Uh, but Murata has more, more options usually. So let's check out multi-layer ceramic capacitors. Their search engine is called Sim Surfing. And so here I select capacitance between 10 picofarad and just 10 picofarad and 15 picofarad, or I guess 15 is higher and here is 10 picofarad. And you can see here is a lot of options. I would say too many options. And they have, for example, 13 picofarad. And they will probably also have 12 picofarad right here. 12. I don't think they have 11. It's a too small step. Oh no, they have also 11 picofarad if you really need. And 10. So as you can see, they have more options. Now I will also select the size, but the problem with the Murata is that the first number here is metric and the second number is inches. So this 0402 is in inches. It says 0.004 inches in length and 0.002 inches in width. And in millimeters is 1 by 0.5. So actually the size that I need is this 1005 in metric or 0.0402 in inches. This is a popular, very small size. The smaller sizes are really hard to handle. You need special equipment. 0402 is the smallest equipment that anyone can handle and which you can also handle with your hands. Smaller sizes are really hard to handle. 0603 is also popular, but now everybody thinks it's even too big. And as you can see, many different voltages. And so basically from Murata, you have more options. But at the same time, it's harder to choose. Okay. So that's about this. Voltage, rated voltage, for example, 10 volts. Oops. 25 volts. Okay, so now I have less options. And I want those that are in production, that are not bad. Okay, so you can see here that I can select 15, 12, or 10. And for example, 12 maybe is the best because the capacitance between 14 and 10, 12 is kind of in the middle. So I would choose this one from Murata. Okay, and now that's the precision. This was something like port B14 and port B15, I guess. Let's see. Just to have a complete picture. $13. So this is how you would connect an external crystal. And as I mentioned, so this high frequency crystal runs in energy mode 0 and 1, and in energy mode 2, it's switched off and you have only this low frequency crystal running. So at energy mode 0, they're both running. And at energy mode 2, only the low frequency one is running. and so on. And more of this you will have an opportunity to do in the labs, which you will have in a couple of weeks. You'll start doing it and you'll see how it can be used. Okay, now I think that's all about the frequency sources and about the precision of internal oscillator. It's also in the datasheet. Oscillator, high frequency RC oscillator. And here again, it's not very precise. If you're running at 14 megahertz, it's from 13.7 to 14.3. External crystals are much more precise. Of course, this thing is also very temperature and voltage dependent. So you can use it, but just not for very precise things. But usually it's sufficient. Usually people use internal oscillator for high frequency and external oscillator for low frequency tasks. And now I can show you one last screen in a second on how this all would look on the PCB. So where is the file?
Why do we use the inner oscillator for high frequency and external for low frequency?
Okay, so because external oscillators cost money, so you want to use as few external oscillators as possible. So internal oscillator doesn't cost anything, it's free, it's built in, but these external oscillators, they cost something like, I don't know, 20 cents, 30 cents, 50 cents. So you don't really want to use external components if you can avoid, but usually the low frequency oscillator is used for clock purposes. And you want the clock to be precise. You want that if you want something to happen at 5:30 p.m., then you want that clock source to be precise so that it doesn't happen something like several minutes later. You don't want that clock to drift away and run 20% faster, so you have only something like 20 hours per day instead of 24 hours per day. So this is why usually the board has this low frequency oscillator for timekeeping, for precise timing. But for other tasks, usually internal oscillator at high frequency is sufficient. But if you need both clocks precise, then of course you would use both of them in a precise manner. So let's check out.
Lower is like more precise, the lower frequency oscillator?
External oscillators are both more precise.
Okay.
It's just that you can kind of tolerate that high frequency things happen with less precision, but low frequency things like clock happen more precisely. So here is a microcontroller, and here are two external oscillators. So this is high frequency, Y3 is high frequency oscillator, and it has these two capacitors here, the load capacitors. So this Y3 is, I think, 48 megahertz crystal with 10 picofarad load capacitances. And this bigger one is the 32.768 kilohertz low frequency oscillator with its two load capacitors. And so they are used. But at the end, the client figured out that this high frequency oscillator is, it's expensive. It costs some like extra 30 cents on every device. So if you manufacture 1000 devices, it's extra 300 euros. So he says, you know what? I don't need that precise internal high frequency oscillator. Let's just drop it. Let's not use this thing. And let's run high frequency tasks from internal oscillator. And only the clock runs from this precise, the second counting or minute and hour counting clock runs from this precise oscillator. So
Okay.
something like this. Okay, so any more questions maybe? So
I have a question, but it's not really about the about this course.
uh-huh.